Hello students, today's class is going to be about unit vectors and dimensions. So most of you must be wondering why are we talking about these things, since these things don't have much weightage in the JEE exams, but these things are the basic building blocks from which you can build up to later things. So let us start. Let's start with units. So what are units? Units are, you can say, units are standards. So let's say you had to measure the length of this sketch pen. You could have measured it with one finger, or you could have measured it with another sketch pen. So it could have been like, let's say, I don't know, maybe 10 sketch pens or something. But then it is not necessary that everyone has this specific sketch pen. So it will not be a standard. So whoever is measuring it, they might come up with a different length. That is why it was necessary to fix standards. So a standard of length is a meter. 1 meter is the standard of length. So this is the length of a piece which has been preserved, or you could define it in terms of speed of light. So this is the distance that light travels in 1 upon speed of light seconds. So now that we know we have a standard unit, now if you say that something is, let's say this line is 3 meters, it means that the length of this line is equal to 3 times the standard length. So this is the standard length and this is 3 times standard length. So this is a unit, and different physical quantities have different units. So let's say a length has, standard for length is 1 meter, standard for mass is 1 kg, standard for temperature is 1 Kelvin, and so on. So there are now among units, these are all units which are very basic. So let's consider another unit, let's call it area. For area, standard unit would be 1 meter square. But if you look at it, 1 meter square is dependent on standard of the length, right? So if the standard of length was, let's say, 1 centimeter, the standard of area would have been 1 square centimeter. So it means that the unit for area is derived from unit of length. So which brings us to another differentiation in units. So units are separated in two parts. One are fundamental units and others are derived units. So fundamental units are those which are independent of everything. Like for example, length. So for length, for a standard of length to be 1 meter, it is not dependent on any other physical quantity. Standard of length is going to be 1 meter no matter what. So the quantities which are independent of other physical parameters are called fundamental quantities, and the units for quantities which are dependent on fundamental quantities. Like for example, we saw area. So area is dependent on length. That is why area is called a unit for area. I mean, unit for area or meter squared is derived from 1 meter. So you can say that this is a derived unit. Okay, so let us look at what all the fundamental units are. So one, for sure, I told you, length. Next is mass. That unit for mass is kg. Next is time. Standard unit for time is 1 second. Next is electric current. This one comes from electricity, field of electricity. So electric current, its SI unit is 1 ampere. Next one is temperature. Its SI is 1 Kelvin. Next is amount of substance. Its unit is 1 mole. And the last is luminescence. Its unit is candela. So these 7 are the fundamental units, and all other units, be it area, be it volume, be it force, be it acceleration, be it anything else, are derived from the combination of these units. So let us look at one example. Let us say we want to find the unit of force in the form of fundamental units. So force can be defined as mass into acceleration, right? Which can be said that mass into distance upon mass into change in velocity upon time, and velocity can be again written as mass into let's say length upon time minus again length upon time divided by time. So if you now let us look at a notation. So for unit of mass, let us write capital M. For unit of length, let us write capital L, and for unit of time, let's write capital T. So if you simplify this, you'll come down to something like mass into length. Now, this is not actually subtraction. We'll look at the properties of dimensions a little later, but you need to understand that L upon T minus L upon T does not equal to 0. It is still L upon T divided by again T and T upon 1. So this becomes reverse and it becomes T square. So mass L T minus 2. So this is the unit of force. So you could say Newton can be represented in terms of mass, length and time like this. In this way, you could represent many other units. Let's consider a couple more examples. So let us find the dimensional formula for surface tension. So how do you write the expression for surface tension? Surface tension T is given by the force that a surface has per length. So force upon length. We just found out the dimensional formula for force. It was mLt minus 2. So mLt minus 2 divided by L. So now here L and L will get cancelled. Again we'll come back to why this is so and why multiplication and division is different than addition and subtraction a bit later. But here L will get cancelled out. So we'll get mt minus 2. So this will be the dimensional formula for surface tension. Now let us do same thing for universal gravitational constant. Let's say the force of gravitation between any two objects is given by universal gravitational constant times mass of the first object times mass of the second object divided by the square of distance between them. Now in this equation you have to find the dimensions of this quantity. So for force we know it is mLt minus 2. G we have to find out. M is capital M. For small m also it is again capital M, and distance square, that is length square. Now on simplifying this we will get m L t minus 2 multiplied by L square divided by m square, which gives us G. So m and square will get cancelled. This will be cubed up. M minus 1 L cube t minus 2 will be the dimension for universal gravitational constant. I hope now you can do this for any other quantity you can find in your textbook. Okay, now let us look at some properties or some uses of of dimensions. So as I told you, let us consider an equation. Let's say t is equal to this is t stands for time period of something. So let's say t is 2 pi root L by G. So this t is time period of a simple pendulum. Okay. So now for this equation, now this equation has been found out experimentally, so we know it is true. There's nothing like, even analytically you can prove this. So this is true equation. So what dimensional analysis tells us that the dimensions of each term, so this is a term and this is another term. So for example, if there was something else in the equation, like for example plus I don't know, maybe again length, this would be the third term. So a term is something that is separated by addition or subtraction. So this is not, these are not two different terms, these are three terms, and L and G can be considered as one term. So the dimensions of each term should be equal for the equation to be true. Now this we've added, this is not a part of the actual equation, I just want to show you. So this t dimension is time, that is done. Now 2 pi is a dimensionless constant, it is a constant, it does not have any dimension, so this does not have, let us ignore this. Then L is length, so square root of L divided by G is acceleration, which gives us LT minus 2. Now if we simplify this, we'll get this side we will get LL cancels out, T goes up, T square, and root of square is T, so T. So LHS equals to RHS. So this dimension is equal to this dimension, which is not equal to this dimension. And you could simply, by not even looking at the physics, you could say that this equation is wrong because dimensions do not match, and that this part is not a part of the equation. So this is the actual equation. So this is one of the uses of dimensional analysis. If you pick up any equation, all the terms in the equation must have same dimensional powers. Now, extending this theory a little bit further, let us say that force of an object, let us say force of an object is proportional to mass and is proportional to, I don't know, length that the force experiences, and is proportional to time t. Now this information can be easily found out experimentally, right? So you don't have to know the exact relation between them. You can just say that force somehow depends on the mass of the body that is applying the force. Force somehow depends on the length. It is not even necessary for you to know that these things have to be true. You are just guessing at this point. Now what dimensional analysis can help us do is find the relation if they are related to each other or not. So for this I want you to look at an example. So let's say the frequency f of let's say we have a pendulum, and the frequency of its oscillation f depends on the, let's say it depends on the force acting on the ball. It depends on the length of the this string, and it depends on the mass per unit length of the string. So I'm just assuming these things right now. F is proportional to force acting on it, is proportional to length of the string, and is proportional to mass per unit length of the string. Let me call it mu. So I'm assuming I'm assuming the nature in which these relations are true. Let's say the small f is proportional to capital F raised to a. A can be 0, 1, -1. That will tell us whether it is related directly or inversely, or it is not related at all. So let us assume for a time that f raised to a. Then let's do L raised to b and mu raised to c. Okay, so what I can write is f is proportional to f raised to a, L raised to b into mu raised to c. Right? To remove this proportionality sign, I'm going to put an equality sign which gives me is equal to k, let's say a constant k, f raised to a, L raised to b, and mu raised to c. Now if we substitute the dimensional formula for all of them and find the relation for a, b, and c, we can actually find the relation in terms of a constant. So let's say frequency is 1 upon time, right? Which means the frequency has a dimensional formula of m raised to 0, L raised to 0, and t raised to -1, correct? Now constant has no dimensional formula, let it go. Force has, as we found out, m L t minus 2 raised to a. Length is L raised to b, and mu is mass per unit length of the string, which will be m L minus 1 raised to c. Okay, now simplifying this side a bit, let the constant go. We are not worried about the constant. Mass raised to, now mass raised to a. Now this does not have mass, so let this go. Mass raised to c. So m raised to a plus into m raised to c. So m raised to a plus c. Similarly, L raised to a plus L raised to b minus L raised to c. L raised to a plus b minus c. And t raised to -2a, no t, and no t. So t raised to -2a, which is equal to m raised to 0, L raised to 0, t raised to -1. Now equate the powers on both the sides. 0 is equal to a plus c. 0 is equal to a plus b minus c. And -1 is equal to -2a. Okay. Now from this equation, because it does not have a zero value, we can find the value of a. So value of a works out to be half, correct? Now let us put this value of a in this equation. So from this, value of c works out to be minus half. And let us put a is equal to half here, c is equal to minus half. So minus into minus plus half 1, and therefore b will be equal to 1, correct? B is equal to 1. Now if we back substitute these ABC values that we found out in this equation, we'll get f is equal to k times f raised to f was raised to a, so a is half, f raised to 1 by 2 multiplied by l raised to 1 and mu raised to minus half. So this we can rewrite this as k is equal to l root of f by mu. So and later by doing experimentation, the value of k was found to be half. So you can find for what this frequency formula holds true. Do that exercise yourself. So k is a constant, L square root f by mu. So we could find the relation between frequency, force, length of the string, and mass per unit length of the string just by using dimensional analysis. We did not need to use any physics at all. That in this way, dimensional analysis can help us find the relation between some quantities. Okay, so that was about units and dimensions. Now let's look at some vectors. Okay, so you must already be knowing that some quantities, like, again, let me use the example of force have directions associated with them. So let's say I have an object here. Applying force on it does not mean that I cannot just say that I have a force of 10 Newton acting on this body, because that does not give me full information. I need what direction the force is acting. So this 10 Newton force is different than this 10 Newton force, and that is different from this 10 Newton force. So these quantities that have directions and magnitudes, so let me rewrite this. So I can call this force as 10 Newton force acting towards the west. So assuming this is the north direction, so this force is 10 Newton to the west. This would be 10 Newton to the north, this would be 10 Newton to the south. So this is the complete notation for how you should write a vector. You should always write a magnitude, its unit, and its direction. So this is what a vector is. A vector is a quantity that has a magnitude. Magnitude, by magnitude I mean the numerical value associated with the quantity, and a direction. Now so a vector, let's say f vector, this is the way you represent a vector. This is the magnitude of a vector. So magnitude of f vector in this case would have been 10 Newton, just 10, not even Newton. F vector means 10 Newton to west. This is how you denote vectors. This is how you show the magnitude of vectors. And there's another thing. This is called a cap. F cap would have been, okay, we'll talk about this later. So this is how you denote vectors. Now let us say we have two vectors with us. This is a force F, and this is a force F1, and this is a force F2. Now if you had to measure the angle between them, how would you do that? Would this be the right angle to measure them, or would this be the right angle to measure them? So to measure the angle between any two given vectors, now this is how you represent vectors. Oh, okay. So this is how you graphically represent vectors. So this line shows a vector acting in this direction of a small magnitude. This line shows a vector acting in this direction in a large magnitude. So the length of the arrow shows the magnitude of the vector, and the direction of the arrow shows the direction in which the vector is acting. So let's say we have these two vectors. How can we measure the angle between them? So for measuring the angle between them, we need to have both the vectors aligned bottom first. Like, you cannot have this arrangement and measure angles. You have to have this arrangement, and then whatever angle is between them, that would be the angle between the vectors. So this is something about vectors. Now let us look at the kind of vectors we deal in physics. So first kind of vector is a unit vector. So we represent that with cap. A cap means this, let's say I have this vector f, and a unit vector f would be a vector in the direction of this vector with a magnitude of unity. So let's say this was a unit magnitude and the direction would be the same, and it would be represented as f cap. Now how do you find a vector with the unit magnitude? Again, we need to learn notations of vectors. For that I'll come back to this again. So for now, let's just understand that a unit vector is a vector with magnitude of unity and direction. Okay, this is the unit vector. Next is a zero vector. As the name suggests, zero, Z-E-R-O. Zero vector, as the name suggests, it means it has zero magnitude. So this vector is a point vector. If you had to represent this graphically, you would represent this as a point. It does not have any magnitude at all. Its direction can be assumed in any direction. Next is the equal vectors. So when can you say that two vectors are equal? So if let's say that these are the two vectors, when can you say that these two vectors are equal? Assume that these two lines have the same length. Like if I had same magnitude, just the same magnitude, like let's say this is one vector and this is one vector, they have the same magnitudes, would they be same? So no, we need to have both the things same, magnitude and direction. So this vector and this vector are equal. This vector and this vector are not equal. Neither are this vector and this vector, they are also not equal. So for vectors to be equal, they need to have same magnitude and same direction. So again, next would be parallel vectors. So vectors which have the same direction are called parallel vectors. Vectors which have opposite directions are called anti-parallel vectors. Then we have something called concurrent vectors. Concurrent vectors are vectors that pass through same points. So this, and this, all these three are concurrent vectors. Then there are coplanar vectors. So let's say these are the two vectors and they belong to this plane. They belong to this plane. They are coplanar vectors. If we had one vector this and the other vector was this, or maybe so, okay, so let's say we have three vectors, 1, 2, and this is the third one. They would not belong to the same plane, and that is when we would say that all the three vectors are not coplanar. Then we have orthogonal vectors. Orthogonal vectors have 90-degree angles between them. But for vectors to have 90-degree angles, what we should do, we should remember that we need to arrange them bottom to bottom first and then check the angle between them. So if they are arranged in this way and they have 90 degrees angle between them, then they are called orthogonal vectors. Okay. Now let us look at how we add and subtract vectors. So let us say that we have a vector A and we have to add it to vector B. You could do that in two ways. You could do that graphically and you could do that analytically. So graphically, let's say this is the A vector and let's say maybe this is the B vector. So first what you need to do is you need to arrange them. The head of this vector should be at the tail of this vector. So let's say I'm arranging them. This is A and this is B. Now if I join A, the bottom of the first vector, to the head of the last vector, this would give me A plus B vector. This is how you add vectors graphically. Let's say if we had maybe three vectors, this is A, this is B, this is C, then this would be a plus b plus c. And you can do this analytically as well. Now this, if this is a vector, and from now onwards I'm writing a as the magnitude of a. So a vector plus b vector can be given by root of a square plus b square plus 2ab cos theta. So cos theta, theta is the angle between the two vectors. So a, b, this is theta, a, b, this is theta. Theta is the angle between the two vectors. A and b are the magnitudes of the vectors. So from this you'll get the magnitude of the resultant vector. And for the angle that it makes, what we do is we find tan alpha. So let's say this is the resultant of a and b, and it makes alpha with b. We'll do we find tan alpha is given by b sin theta divided by a plus b sin theta. So again, a and b are magnitudes and theta is the angle between the vectors. This will give you, sorry, this is cos theta. So this will give you the value for tan alpha, and if you do tan inverse of this, you'll get the angle between b vector and the resultant vector. Now, similarly, if you had to subtract vectors, the analytical method would change very minutely. This would become minus. Everything else stays the same. But graphically what changes, so now one more thing I had to tell you was a vector plus b vector is equal to b vector plus a vector. Addition of vectors follows this, but subtraction is not the same. A vector plus b vector minus b vector is not equal to b vector minus a vector. So I'll tell you how this works graphically. So let's say this is a, let's say this is b. If we do this, we will get a minus b. Oh, sorry. Let's say this is a and this is b, and if we do this, we get a minus b. And if this is a and this is b, we get b minus a. So a minus b and b minus a have the same magnitude but opposite directions. So in vectors, if these were scalars, by scalars I mean the quantities which have just magnitude, if these were scalars, it would have been minus c or plus c. But for vectors, there is no such thing as minus. For vectors, if you change the order of subtraction, you get opposite direction vectors. So this was about addition and subtraction of vectors. Now let's look at multiplication of vectors. Okay, this was again a small mistake. So let me tell this to you: a, b, and this would be a minus b, and this would be b minus a. Now let's look at multiplication of vectors. So when we multiply vectors, there are two possibilities. So there are two types of multiplications we can do with vectors. One is if we multiply two vectors and we get a scalar quantity as their product. That is called the dot product. And the second is when we multiply two vectors and we get a third vector as the result of them. That is called the cross product. Now we represent them also in a similar way. So a dot product can be represented by a dot b, and a cross product is represented by a cross b. That is why their names are dot product and cross product. So let's look at dot product first. Now There's one more way to represent vectors. So first we saw was graphical, then we saw that a vector is this and magnitude of a vector is this. There's another way. A vector can be written as a1 I cap plus b1 j cap plus c1 k cap. Now I cap, j cap and k cap are unit vectors in the respective directions of x axis, y axis and z axis. So I cap, j cap and k cap. So and let us suppose that this was my vector A. The component of vector A in the direction of I cap, that is a1 in the direction of I cap, similarly b1 in the direction of j cap, and similarly c1 in the direction of k cap. This is another way you can represent vectors. So in the case of dot product, a dot b can be given by a b cos theta. This is the representation which we did here. So a is the magnitude of a vector, b is the magnitude of b vector, and theta is the angle between them. So let's say a and b are two vectors and you have to find the product of these vectors, scalar product of these vectors. You would do magnitude of a multiplied by magnitude of b multiplied by cos of theta, cos of the angle between them. And if the vectors were in this form, let's say a is given by a1 I cap plus b1 j cap plus c1 k cap, and b is given as a2 I cap plus b2 j cap plus c2 k cap. If the vectors were given in this form, how would we do the dot product? So a dot b would be given by the product of, so when we multiply vectors like this, what you have to do is multiply a1 with a2, then a1 with b2, a1 with c2, then you would multiply b1 with a2, b1 with b2 and b1 with c2, and then c1 with that whole multiplication you had to do. And now what you need to understand is I and j are unit vectors in x and y axis, as we discussed earlier. So let's say this is I cap vector and this is the j cap vector. So these are vectors, and as we've seen that to find their product, what we do is their magnitude. So these are unit vectors, so their magnitudes would be 1, and the cos of angle between them. So their angle between x-axis and y-axis is 90 degrees. So angle between I cap and j cap would also be 90 degrees multiplied by cos theta, that is cos 90. Cos 90 is 0. So what happens is when you multiply, unlike unit vectors like I into j into k or j into I or j into k, when you do that, it turns out to be 0. So when we are multiplying, when we are doing a dot product, we just multiply similar unit vectors. So this would become a1 into a2, a1 into a2, and I cap into I cap would be 1, plus b1 into b2, j cap into j cap would be 1, plus c1 into c2, k cap into k cap would be 1. So if a vector is given in this form, this is how you do a dot product. Now let's look at similarly let's look at how you do a cross product. So a cross b, a cross b in this form, a1 I cap plus b1 j cap plus c1 k cap. This is a vector, and b vector is a2 I cap plus b2 j cap plus c2 k cap. Now these are the vectors given to us. How do we do the cross product? So for doing the cross product, what we do is we find the we arrange the determinant. So I cap, j cap and k cap, and a1 a2, b1 b2, c1 c2. This would give us a cross b vector. So if we solve this determinant, we'll get the a cross b vector. But remember, a cross b vector has magnitude and direction both. So let's say in this case we did not have to find direction. So whatever answer we got from this would be the magnitude. So in this case, this would give us the vector, and that would be, now how do we solve this? b1 c2, B1 C2 minus C1 B2 I cap plus A1 C2 C1 A2 minus C1 A2 J cap plus A1 B2 minus A2 B1 K cap. So this would give us a vector, and that is what we want. So and in this form, when we do the cross product, let's say we have been given A as magnitude and direction and B as magnitude and direction. In that case, A cross B would be A B sine theta, A B sine theta, and this would give us the magnitude of A cross B, and direction of A cross B would be, we would find by right hand thumb rule. So A cross B would be A from you would align your right hand to the direction of A. Let me draw it a little bigger so that you can see. Let's say this is A and let's say this is B. So you would align your right hand along the first vector. If we had to find A cross B, you would do A first and curl your fingers towards B. Then your thumb would give you the direction of A cross B. So that would be into the plane. Now if we had to find B cross A, now you would do align your right hand to the vector B and curl your fingers towards A. That would give us out of the plane. So if you are given vectors in this magnitude and direction form, what you do is you do AB sine theta, that gives you magnitude of A cross B, and you find the direction by using the right hand thumb rule. Now, let us solve a small problem about multiplying vectors. Say we have two vectors, A is 2 I cap plus 3 j cap and k cap, and B is I cap minus j cap plus k cap, and we have to find the dot product of these vectors, cross product of these vectors, and unit vectors in the direction of A and in the direction of B. Now let us do it stepwise. Let's find the dot product first. So to find the dot product in this form, what we discussed earlier, what we do is we just multiply the directions, multiply the magnitudes of individual directions. So A dot B would be given by 2 into 1, that is 2, 3 into minus 1, that is minus 3, and 1 into 1, that is plus 1. So A cross B would be, A dot B would be 0. And in this case, we don't have to find the direction because dot product gives us a scalar answer. So A dot B is 0 in this case. Now let's find the cross product. Now if vectors are in this form, how do we do the cross product? So A cross B will be given by determinant of I, J and K, and we arrange the first vector 2, 3, 1 and 1 minus 1, 1. Now if we find the answer of this determinant, that will give us the A cross B vector. So the A cross B would be 3 into 1, 3, minus 1 into 1, minus 1, and minus of minus 1 plus 1 I cap, plus 2 into 1, 2, 1 into 1 minus 1 into j cap, this would be minus, and plus k into 2 into minus 1 minus 2, and 3 into 1 minus 3 into k cap. So this would give us 4 I cap minus j cap plus minus 5 k cap, minus 5 k cap. So this is the answer of cross product of A into B. Now to find unit vector in direction of A and B. Now how do you find unit vectors in direction of A and B? Now let us say I want to find the unit vector in direction of A. So we start with the vector A. So A is given as 2 I cap plus 3 j cap and 1 k cap. So first we find the magnitude of A, which is given by 2 square, that 2 square plus 3 square plus 1 square. That would be equal to 4 plus 9 plus 1 root 14. Now a vector, now you again write a is equal to 2 I cap plus 3 j cap plus k cap. Now if we this is the vector. Now as we defined earlier, a vector a cap, a unit vector in direction of a is given by a vector divided by magnitude of a, right? Now for this we already found the magnitude of a, so a cap would be 2 by dividing this magnitude of a, that is what we found. Okay, one thing you need to know is when you multiply or divide scalars, scalars with vectors, what happens is, let's say I have a vector a and I'm multiplying it with a scalar n, it just gets multiplied. It changes the magnitude, it never changes the direction. So whatever multiplications we are doing, that happen with the magnitude. So in this case we have a division, and the division is by root 14. So 2 divided by root 14 I cap plus 3 divided by root 14 j cap plus 1 divided by root 14 k cap. This would be the unit vector in direction of a. And very similarly, you can find a unit vector in the direction of b. That would be, let us find the magnitude of b first. Magnitude of b is given by root of 1 square 1 plus 1 square, so that would be root 3, and b cap would be I cap by root 3 minus j cap by root 3 plus k cap by root 3. This would be the unit vector in direction of b cap. So this is all about units, dimensions and vectors. Mostly you would learn much more advanced things regarding to vectors in your mathematics classes. This is the basic things that you need to know as far as physics is concerned, and JEE exams very rarely ask questions about vectors in physics subject. It happens very rarely. So this is just to build your basic understanding of how other vectors in the chapter are going to work. So that is all. Thank you.